All right, in this section, section 13 of chapter 23, we are going to talk about doing substitution reactions with Aryl diazonium salts. We saw in the previous video how to make these diazonium salts using the nitrosonium ion reacting with amines, reacting with aniline, in particular, aniline derivatives. Well, now what we want to do is we want to look at what kinds of reactions can we do with those diazonium salts. So they tend to go under two reactions. One of the types of reactions is where we do a substitution reaction of the N2 with some group. And it can be a group of atoms or it can be a single atom. And so we're going to look at those here. That's what we're going to look at here next. That's what the point of this section is. In a later section, we're going to talk about a coupling reaction that can occur between the diazonium salt and another benzene, and it helps if that other benzene has a very strong electron donating group, like an aniline or aniline derivative, or a hydroxy group, or a methoxy group, or alkoxy group, any of those that are strong electron donating groups. We can get this kind of Azo compound. We're also going to talk about what they use these Azo compounds for. Because they're so highly conjugated, they tend to absorb in the visible part of the spectrum, which means they tend to have colors that are not just yellow or colorless. They tend to have some bright colors to them. So we'll talk about those here in a bit, but first let's look at substitution reactions. There's some pretty cool substitution reactions that you might not have thought possible before. All right, now the mechanism does vary with whatever the identity of our replacing ion is going to be, but so we're just not going to look at the mechanism for now. What we're going to do is we're going to talk about what product do you get when you treat it with a certain kind of compound. So if you take a diazonium salt and you react it with water, you can produce a phenol. All right? That is an incredibly useful thing to be able to do. So if you have this where it was an aniline, you converted it into a diazonium salt, and now you've turned it into a phenol. That is a very useful transformation to be able to do. Let's look at another one. There's a reaction where you can do this with chloride, so copper 1 chloride. You can produce an Aryl chloride. This is in the category of reactions that we call a Sandmeyer reaction. So it's a Sandmeyer reaction. And there's another halogen we can do this with here in a minute, but if we react this with copper 1 chloride, we can get an Aryl chloride. So again, that gives us a way to switch the functionality of a particular group. All right. Here I've got copper 1 bromide, and I've numbered this one too as well because it's essentially the same reaction as the one with the copper chloride. It's just copper bromide instead. So I call this number 2 as well. Also a Sandmeyer reaction fits in that category of reaction, and we get an Aryl bromide. We can use fluoroboric acid to form an Aryl fluoride. And you may be thinking, fluoroboric acid, that's not one I'm very familiar with. There's probably a reason you're not familiar with it. It's not something that you have just sitting around in most laboratories. You really need to know what you're doing if you're going to work with fluoroboric acid. So there we can fluorinate this and turn this into the Aryl fluoride. Again, that is something that we haven't had a lot of reactions that show how to do this. If we want to make an iodide, we can simply use sodium iodide or potassium iodide to form the Aryl iodide. So now we've got ways that we can make the chloride, the bromide, the fluoride, and the iodide. All right, so we have all of our options available for our group 7 halides. Another possibility is we can use copper 1 nitrile or copper 1 cyanide. Copper 1 cyanide can be used to produce benzonitrile. So this technically falls in the Sandmeyer reaction category. So if you go and look up Sandmeyer reaction, you will find this one included. And so again, we're going to replace that N2 with this nucleophile. So we'll end up with cyanide. or the benzonitrile. This next one seems like, well, that's an odd thing to do, because normally we're trying to add functionality to a group, but to take something like an amine and then convert it into benzene, that doesn't seem to make sense. And if this is all you were doing, if you were just taking your amino compound, you created the diazonium salt and then converted it into benzene, that by itself doesn't make a whole lot of sense. So at first glance, you may be thinking, why would we do this? What is the point of doing this? Well, I'll tell you, the point of doing this is not so that we can just make benzene. It's so that we can make some reactions, do other reactions on this where we use our ortho para director, the aniline, to put stuff on here and then remove the NH2, convert it into diazonium, convert that diazonium into hydrogen, and then that gives us a functional group we otherwise wouldn't have been able to do. I will show you examples of that in a few minutes, so stay tuned. All right, we're going to look at number 60. On number 60, let's go back over here. All right, so on number 60, we want to see what happens when we do each of these. And so it might be helpful to figure out what's going on here. If we treat it with H2O, H2O is going to produce a phenol. That phenol we can then deprotonate, and then when we treat it with methyl bromide, we're going to get the methoxy group. So we will convert that into that. So that is the answer for part A. All right. Here, when we use the copper 1 cyanide, that's going to convert this into the nitrile. So we'll have benzonitrile, chlorobenzonitrile. Dibal, this is where you need to know your reactions from previously. Dibal will convert the benzonitrile into an aldehyde, and then the H2O is simply to work it up. So this is going to give us this metachlorobenzaldehyde. All right, and then this particular reaction here, we've got this aniline. Aniline will react. So the aniline will react with this to give us a diazonium salt, and then we use this to convert that aniline into the acetanilide. All right, excuse the noise in the background. A neighbor has decided to run their lawnmower. I don't know that they're actually mowing. I think they're just using it to mess up my recording. So here we'll have NH, and then we've converted that into the acetanilide. And so we can make that particular compound using this reaction sequence. All right, so let's look for a practical application for why would we want to convert our amino into a diazonium and then into a hydrogen? What sequence of, what logic could we use for that? Well, the logic is, what if you wanted to make this particular compound? What if you wanted to take benzene and convert it into 1,3,5-tribromobenzene? Well, there's no direct way of doing that. If you take benzene and you attempt to do halogenation, as we talked about previously in that chapter on reactions, the electrophilic aromatic substitution reaction. Bromine is an ortho para director, and so once you put one bromine on there, subsequent bromines would go in the ortho and para positions. You wouldn't get this meta situation going on. So the way we could use this potentially would be to start with our ortho para director aniline, all right, which is a very strong ortho para director. put it in the presence of bromine and iron 3 bromide, and we would get this tribromoaniline, so the 2,4,6 tribromoaniline. And then we could use that sequence of reactions where we convert this aniline into a diazonium and treat it with the hypophosphorus acid, and that would give us this compound. Isn't that clever? I think that's extremely clever use of that kind of chemistry. So let's look at the full synthesis of 1,3,5-tribromobenzene using this methodology. First, we can start from all the way from benzene. And if we start all the way from benzene, then the reaction will look like this. We'll do nitration of the benzene to give us our nitrogen on the benzene. So we'll have nitrobenzene at that point. We can reduce that nitro group to the aniline group using catalytic hydrogenation. We've talked about that. There's a couple of different options we can use for this, but we're just going to look at the catalytic hydrogenation. Then we could use bromine and the iron 3 bromide to produce that tribromoaniline. We could convert this aniline into the diazonium salt using the sodium nitrite with HCl. That would give us the diazonium salt. And then finally use the hypophosphorus acid, the H3PO2, to replace that diazonium ion with hydrogen, and we get our product. Again, I just think that's incredibly clever, very cool set of reactions. And so using a similar methodology, we can convert any nitro compound, do various reactions, and then convert it into something else at the end, which reverses our ortho-para-directing or makes it possible that we have a substituent on there that we couldn't have used for various reasons. And so let me explain here. So you do nitration, reduction, dietization, and then substitution. And at any point along the way, there are potential reactions that you could have done on these. And then when you remove this or convert it into something else, it looks as though you have done something that seems impossible. So it unlocks a much larger range of possibilities to our electrophilic aromatic substitution reactions that we talked about back in chapter 16. It gives us a lot more tools. So anything that gives us more options is really good. So let's look at this. So here I've got a couple of reactions where we're going to start from aniline and we're going to make each of these. So we're going to start from aniline and we're going to make each of these. On these, some of these I have come up with myself, and other ones I have found. So other ones I have found looking at some other possibilities. So let's just kind of go through this and see how it is we could make these things. All right. Well, so chlorination, when we do chlorination, that's electrophilic aromatic substitution. This is an ortho-para-director. So potentially we could do this and then this, or we could take aniline, since we're starting with aniline. We take aniline, add the chlorine to it, and then modify our NH2 to get us to this. And you may be thinking, well, how do we get from our NH2 to this? Like, what is it that we would be making? And again, there's more than one possible way to do this. So I'm going to take you through one possible synthesis pathway here. So we're going to start with aniline. So there is our aniline. We can convert that aniline into the chloroaniline. So use Cl2, and I'm not going to use the FeCl3 because if we use FeCl3, we're going to get 3 chlorines on there, and we just want the 1 chlorine. And so I will put NH2 and chlorine. And at this point, I feel obligated to point out that we wouldn't just get the para, we would also get plus ortho. And the reason I mention that is at this point, you would have to do some, probably some chromatography to convert, to separate out the ortho from the para. I think if you don't do this, you're kind of leaving out a critical part of your synthesis. So, all right, now that we've got that, we've got the chloro group, we just need to convert this into this group. And that at first doesn't seem very viable, but we're going to make this into the diazonium salt. So we'll use the sodium nitrite and HCl, and that will give us a diazonium salt, so N2 plus Cl minus, and then our chloro group. And then we can use that copper cyanide. This is that a variation of the Sandmeyer reaction that I mentioned earlier. All right. There's a couple of options we can do with this. We could convert this into an aldehyde. We can convert it into a carboxylic acid. We can convert it into an amide. However, we can't convert it directly into this amide. And so if we convert it into an amide, we could potentially deprotonate that amide and then do a substitution, although that's a little iffy. But we could take this, hydrolyze it, and convert it into a carboxylic acid. So once it's that carboxylic acid, we can then react this with CH3NH2. And if you use this, then you need 2 equivalents of this and you just heat it up. Or you could use this and DCC, the dicyclohexylcarbodiimide, which we saw in an earlier chapter, chapter 20, I think. We'd get that NHCH3, and then the chloro would be here. And that is a viable synthesis for this molecule. All right. If you come up with, you think, what is a more elegant synthesis, drop me a line, send me a comment. And I think I'm almost certain there are probably easier ways to do it, but I think this is a viable way to do it. All right. For this one, we've got an alkyl group and a bromo group. So an alkyl group and a bromo group. And so here, bromo is an ortho-para director, and the alkyl group is also an ortho-para director. And so you may be thinking, well, how can we get this to work? What is it that we can do to get this to work? And the answer is, it's tricky, but we're going to again start with our aniline, because that was what this required, and that's what the problem required, is to start with aniline. So we'll start with the NH2, and then with that, we could use bromine, much like we used chlorine in the previous one to get the monochlorinated, we could use bromine to get the monobrominated. And when we do this, we would get a mixture of ortho and para. I'm going to write the ortho version of this, so bromine, but it turns out the para would still be synthetically useful. So, all right, now we're going to take this, and we're going to react it with, acetyl chloride, so CH3COCl, and that's, and here I meant to put plus para. So we would get the para isomer there, and we either need to separate or deal with the consequences. So we could get the acetanilide version of this, so NH, and then bromo. And then we could do Friedel-Crafts alkylation. And when we do Friedel-Crafts alkylation with CH3Cl and aluminum chloride, that would give us this isomer, but we could also get the isomer where the alkyl group is there, and it turns out both of those would also be synthetically useful. All right, so I'm going to take this. Oh, I forgot to put the methyl group there. I'm going to take this and rewrite it down here. And there's our alkyl group. All right, we can now hydrolyze this, and we could do it as either acid hydrolysis or base hydrolysis. I'm just going to write it down as acid hydrolysis. So that acid hydrolysis would give us the aniline. All right, and then this we could convert into the diazonium salt using our diazotization conditions, where we have, let's see, the sodium nitrite and HCl. Okay, and then finally we can take that and treat it. We can take that and treat it with hypophosphorus acid. So H3PO2, and that would give us our product. Give a bromo there, and meta to that, we would have a methyl group. All right, now a couple of notes about this. Again, if you got the para isomer here, that para isomer, you could do the same reaction and you would have the para isomer. And when you do the Friedel-Crafts alkylation with that para isomer, you would have gotten the methyl here and the bromo here. Well, it turns out those are both, when you go through the remainder of the sequence, those are both going to give you the same product. So even though this gives you more than one isomer and this alkylation also gives you more than one isomer, all of those, if you carried through, all of those would give you this as the final product. Now, when you're doing this for the first time, you probably would isolate each of these and go to the end. But if you were doing an industrial application, you might keep all those other isomers in there because they all give you the same product. Just depends on how cleanly it worked. Okay, go back over here. We're going to finish out this chapter. We're going to talk about the coupling reactions that occur between the aryl diazonium salts and then with the aromatic rings that have strong electron donating groups. So the strong electron donating groups, they can either be oxygen or nitrogen containing groups. So either the aniline derivatives or the alcohol or the alkoxy. We don't have the alkoxy listed there. All right. So we can do this reaction where we will get a reaction between the nitrogen on the end, and this para position. And so we will get this azo coupling. That azo compound, that is the product here, is highly conjugated. And because it's highly conjugated, it's probably going to absorb in the visible part of the spectrum. And that means when it absorbs in the visible part of the spectrum, it will have some color to it. That color will depend on what the substituents are. The one that we have here, if we use this dimethyl aniline here, the N,N-dimethyl aniline, as our coupling agent or coupling compound, we can get this one, which is called butter yellow. And it has that distinct yellow color that butter almost has. All right. It is a little bit different than the color of butter, but it has that butter color, the yellow color. Interesting about this. There's a product that was originally made, way back in the 20th century. I don't remember exactly when, 60s, 70s, something like that. And it was where they would take vegetable oil and they would convert the vegetable oil. They would do some partial hydrogenation to it and turn it into a solid, but not a very hard solid. And if they put some flavoring in it, it would taste like butter. And then if they put this compound in it, it made to look kind of like butter. The problem with the margarine when it didn't have this in there is that it was white. And to use white butter, that just seems kind of weird. And so they add this dye, which is also kind of weird. But there you go. This can be used to make margarine actually look more like butter. I prefer just using butter. All right, so let's look at that Azo coupling mechanism. So we can do an Azo coupling mechanism where it's an electrophilic aromatic substitution, and the diazonium salt is acting as our electrophile. So that nitrogen has a partial positive character because of this positive, which means we can do electrophilic attack on this aromatic ring. And the only reason we can do this is because we have this strong electron donating group. So we get the diazonium salt acts as an electrophile. We get a resonance stabilized carbocation. So there's additional resonance structures that we can draw there. One of those resonance structures has to have resonance electron donating, which is why we need that strong donating group there. And then we lose a proton. Something comes along, deprotonates. In this case, chloride, maybe. All right, so we deprotonate and we get our diazonium salt. We regenerate our aromatic ring. There is our not diazonium salt, our diazo compound. So our diazo compound. So there's all kinds of dyes that have been made this way. All kinds of compounds that have been made this way. Let's look at a couple of facts about Azo coupling. Because the diazonium salt is only a weak electrophile, that's why we need those strong electron donating groups. If we didn't have those strong electron donating groups to activate the ring, the reaction just doesn't happen very well. So also, these groups tend to be ortho-para directors, but because of the size, we tend to mostly get the para substituent. And the only way where we don't get this in the para position is if we have a substituent there already. But in most cases, this will go into the para position instead of the ortho position. So that's kind of convenient because that means you get limited stuff that you have to separate out. All right, so when we're doing synthesis of an azo compound, let's look at an example. So what do we need to do to make this particular azo compound? Well, we can think about this in a couple of ways. We find our azo group, our nitrogens here, and then find the aromatic ring that has the strongly electron donating group, which is this. And that means that this particular bond is the new bond that we made when we did the azo coupling. So if we break it apart there, this would be our diazonium salt component, and this would be our ring that has the electron donating group. So we'd have this as our diazonium salt, and then this part would be our ring with our strong electron donating group. So with this methyl orange, if we wanted to synthesize this, again, we break it there. This particular part of the compound would be our diazonium ion that we start with, and this particular part would be our aromatic ring with the strong electron donating group. All right, so on number 70, I'll tell you the issue with number 70 is that I didn't put enough space. And so what I'm going to do with number 70 is that I am going to use some just regular lined notebook paper to do these. I will bring in the piece of paper. All right. Let's move down here. So there's number 70. And I just didn't leave enough room to do all of this. So I'm going to redraw this on a piece of paper. And after I redraw this on a piece of paper, then we're going to do the synthesis on that piece of paper. And that will give us a lot more room to work with. So the questions say, synthesize each compound from benzene. So starting from benzene is like, oh, derive this equation from first principles. If we have benzene is readily available, and so we need to figure out how to get these substituents on using our knowledge of electrophilic aromatic substitution that we learned back in chapter 16. And then use our recent knowledge to figure out the extra tools that we can use to get these particular compounds. So let's do that. I'm going to pause, and then next thing you're going to see is this compound on a piece of regular paper. All right, there we go. So I copied that over, and just so you can see that this is the same thing, here you go. I've got that same compound. All right, and we want to make this from benzene. All right, so we'll start with some benzene. All right, so there is some benzene. Now, there's more than one way to do this. And in fact, every one of these reactions, A, B, and C, there's going to be more than one possible pathway to do this. And in fact, there's probably pathways that I have not even thought of that somebody else will think of. And if you think of a clever one, send it to me. So the very first thing I'm going to do here is a Friedel-Crafts alkylation. All right, so Friedel-Crafts alkylation to give us toluene. So CH3 there. So we have that toluene. All right, that toluene we can do nitration on. So if we use HNO3 and H2SO4 nitration conditions, we can get our para-nitrotoluene. Now, again, I do feel obligated to mention that we would also get the meta isomer. You would also get the meta isomer. I also mentioned that if you do this and you raise the temperature to high temperatures and you do this reaction multiple times, you can get trinitrotoluene, which is an explosive. I will also mention that you really, really have to know what you're doing, and you need a very good personal protective equipment, and you need blast shields and things like that, because the product that you're making would be very explosive, and you're heating it up while you're making it. It's not a trivial thing to do. And there have been many people who know exactly what they're doing and have had explosions occur. So don't attempt to do that on your own. It doesn't accidentally happen, because every time you add a nitro group, it gets less activated. So anyway, I just mentioned that because it's kind of cool. All right, we're going to take that nitro group and we're going to hydrogenate it. We will just use catalytic hydrogenation methods, although you could, we want PD, not PB. So we want palladium on carbon. So catalytic hydrogenation methods. But as I mentioned, you could use iron with HCl or tin with HCl. There's a couple of options that are available. So we're doing catalytic hydrogenation that will convert our nitro group into an amino group. All right. Now that we have that amino group, we're going to convert this into the diazonium salt. I'll go ahead and redraw that. So CH3 NH2. We'll convert that into the diazonium salt using the sodium nitrite and HCl. Okay, so now we have that diazonium salt. We can convert that diazonium salt into a nitrile using the copper 1 cyanide. I have seen situations where people have used sodium cyanide, and I don't know that I don't know if that is an additive. I think you need the copper 1 cyanide. I would have to look at that more closely. I think I would need to do a search on that. But copper 1 cyanide is how it goes via the Sandmeyer process. So we'll get that cyano group. And now we're just one step away from creating this original compound. And that is, we can turn this cyano group into a CH2NH2 group by doing reduction with lithium aluminum hydride. And follow it up by working it up with water. And we will get our final product of this. All right, so that is a pretty cool synthesis. And as you can see, if I had attempted to put that all onto here, it would have been really scrunched up. So that's why I put it onto regular paper. All right, now I'm going to put this onto the same piece of paper. And so I'm going to pause it while I write that down. And so that way you'll see this here in just a second. All right, so there we go. We've got this benzoic acid with an ethyl group in the para position. All right, so again, I think a similar methodology to get an alkyl group, like similar methodologies to what we did up here. Get an alkyl group on there to begin with. Do the nitration, convert it into the diazonium salt, and then use that diazonium salt to convert into this carboxylic acid. So if we use a similar methodology and go all the way to a nitrile, where we have an ethyl here, we can do hydrolysis of the nitrile, and that will give us that carboxylic acid. So that's the approach I'm going to take with this one. So again, we'll start with benzene as per the problem. This time we're going to use the CH3CH2Cl. So we'll use that as our alkylating agent, and then aluminum chloride. And so that's going to give us the ethyl benzene. All right. With the ethyl benzene, we can then do nitration. All right, and that would give us that particular compound. Just like what we did above, we can do catalytic hydrogenation here. So H2, palladium on carbon, and we can get the aniline derivative. So it'd be the paraethyl aniline. All right. I'm going to take that and just rewrite it down here. And if we treat that with the sodium nitrite and HCl, we can convert this into a diazonium salt. All right, so now we have that diazonium salt. And with that diazonium salt, we're going to do exactly the same thing we did on the previous one, which is where we treat it with the copper cyanide. All right, when we treat it with the copper cyanide, we'll convert this into paraethyl benzonitrile. And then this we can convert directly into this carboxylic acid by doing acid catalyzed hydrolysis. So H3O plus, and we'll do the acid catalyzed hydrolysis, and that will give us that carboxylic acid. And that would give us that compound. So pretty cool synthesis. Again, if you come up with a clever way, more clever way to get to this, let me know. I can definitely think of some other options. I mean, we could We could make a bromide here and then treat that bromide, turn that bromide into a Grignard reagent and then treat that with CO2. But I think that that's going to be maybe a lower yield than this because we're going to have more steps. All right, for our final one is going to be to make this Azo compound. So this Azo compound. So clearly we're going to need to get these chloros on here, the diazo. There's going to be some stuff that is involved in making this step. I will assume that we already have aniline because we've made aniline. I've shown you how to make aniline already. Well, we'll need to go through the process of making aniline, but I'm going to put this onto a piece of paper. So I'm going to pause the video while I do that. All right, so here is our desired product. We're going to start with benzene. So I'm going to start with benzene right here. And we're going to convert that into nitrobenzene using the nitric acid and sulfuric acid. That's our electrophilic aromatic substitution, nitration, chapter 16. We're going to convert that into aniline. All right. And we'll do that again by catalytic hydrogenation. All right, so catalytic hydrogenation. We're going to use that aniline later, but once we've made it, we don't have to show how to use it, how to make it again. And then we're going to take that and convert that into acetanilide. All right, so there we've got acetanilide. All right, so with the reason we did that is because we want to protect this because we're going to do a nitration next that has strong acid conditions, and so we're going to do a nitration next, and we're also going to do some other reactions that would potentially damage this. So let's go ahead and rewrite that, which is our acetanilide. And we're going to react that. Again, we're going to do nitration. So HNO3 with H2SO4. All right. This is also going to give us the meta. So I'm going to go ahead and put plus meta. Not meta, plus ortho is what I meant to say, plus ortho. All right, so we're going to get plus the ortho. That means we'd need to do some separation here. No big deal. All right, and then with that, we're going to treat that with, to get our 2 chlorines on there, we're going to put Cl2 and FeCl3. Now, I'm not sure if this particular reaction would be hindered by having aniline instead of the acetanilide, but I'm pretty sure this one would react with the aniline. And so it's probably best that we protected it anyway. Here, with that chlorine, we could add 2 chlorines on there. So NH, carbonyl. Down here, we still have the nitro. And then here, we've got Cl. All right. We're now going to convert, we're now going to hydrolyze. We're going to hydrolyze this. And when we hydrolyze that acetanilide, we're going to get the aniline. And again, we could do this with acid or base. I think I'm going to choose base here. So H2O and hydroxide. Give us NH2, Cl, Cl, and nitro. All right. With that, we're going to convert that aniline into the diazonium salt. And we'll do that using our sodium nitrite and HCl, and it'll convert the aniline into the diazonium salt and leave these other things intact. All right. That diazonium salt, we're going to convert that into hydrogen. And that's because we don't want anything here. We wanted to convert that into hydrogen. And we'll do that using our hypophosphorus acid, so H3PO2. All right. Now, we're into the home stretch because I think here at this point, if I'd given you this compound, you could have made this compound really pretty easily. I think this is the hard part, is to figure out how to get these three substituents on there. So how to get those three substituents on there without, well, just how to get them on there, because that is a somewhat tricky thing to do. Suppose you could do nitration and then attempt to do halogenation. That would get you the meta position, but then our next one would end up either ortho or pair. It would be tricky. It'd be tricky. So this is probably our best pathway. Okay. We are going to convert this particular compound into the aniline. And again, we will use catalytic hydrogenation. So H2 with palladium on carbon. It'll convert this into an aniline. That dichloroaniline, to be specific. All right. And then that we can convert into the diazonium salt with the sodium nitrite and HCl. I'm going to go ahead and put this down here. And I'm going to raise this up a smidge so I have a little bit more room. All right. So now we're going to have the diazonium salt. That diazonium salt, we can now convert, we can now react that with aniline. We made aniline up here, so we can react that with aniline. Okay. And when we react that with aniline, we're going to get our final product. So this nitrogen is going to react with the paracarbon on here, and we will get our final product. And I'm going to draw it sideways so that it's easier to see here. So Cl, Cl, nitrogen, double bond nitrogen. NH2, and that is our final product up there. So, pretty cool synthetic pathway. All right. Now that we've done that, let's go back and we're going to finish up the last little section in this chapter where we talk about synthetic dyes, and we also talk about sulfa drugs, which is it's a cool story. So, all right, up until the middle of the 19th century, pretty much all dyes that you use to dye clothes and fabrics and stuff were natural dyes. They were things that were isolated from either plants or animals or minerals or whatever. Some of those plants and animals were actually kind of rare, and so isolating them would not have been a trivial thing to do, and in some cases might have endangered some of those species. So I don't think the indigo plant is at risk, but if you wanted to get that blue indigo color, you needed to isolate it from the indigo plant. This Tyrian purple you could get from a particular sea snail that is in a Mediterranean sea snail shell. Say that 5 times fast. And then you could get this from this particular plant. You could get the alizarin, which is a bright red color. But there were limited options. There just wasn't a whole lot you could do for dyes. And that was until 1856, so the middle of the 19th century. And so the very first one was called Mauvine, and based on the name, you can guess it was a mauve or kind of purplish color. And so this chemist, William Henry Perkin, accidentally produced Mauvine while trying to make quinine. And if you look at the structure of quinine, you may be curious how you get from quinine to this, but this is the structure of Mauvine. This is a minor component of it, and you'll see the difference here is just we've got an alkyl group. And it's kind of amazing how putting an alkyl group can change the color of something. So just adding one little substituent can change the color of something, but it can. Anyway, it's a beautiful color. So there is a sample of the Mauvine, and here is something that has been dyed with that Mauvine, and that's just a lovely purple color. And so that was the beginning of a revolution in preparing synthetic dyes. And so chemists started doing all kinds of manipulations to different conjugated compounds in order to get different colors. All right. And in doing so, they learned a lot about chemistry. So they actually learned quite a bit about how chemistry works. So here are a couple of synthetic dyes that have been made over the years. This one is called Para Red. Again, it uses an Azo coupling. It's an Azo dye. Here is Congo Red. All right, and you can see here it's got 2 Azo couplings. All right. But you can tell they all have very highly conjugated systems. And when you have highly conjugated systems, it shifts the absorbance from the ultraviolet part of the spectrum into the visible part of the spectrum. And when you shift it to the visible part of the spectrum, then you can get things that have bright colors. Right. Now, kind of on a side path, and this was one of those serendipitous things as well. It was sort of accidental. In 1935, there was the invention of the first synthetic antibiotic. And so a German chemist, or a German physician, had a daughter who was sick, and he gave his daughter Pronocil, which was an Azo dye. So she had strep throat, essentially, and there was no real treatment other than just to sort of wait it out. And back then, when people waited it out, some of them died. And so because he didn't want his daughter to die, he gave her Pronocil, which is an Azo dye that had shown some activity in inhibiting the growth of bacteria in mice. Well, thankfully, his daughter recovered. The Pronocil apparently helped and helped to kill her infection, and didn't kill her, thankfully. And so she survived. And that was the first known use of what we call sulfa drugs for treating bacterial infections. So turns out, all right, the company that made Pronocil was like super excited because they once they found this out, it's like, we have an antibiotic. And so, they had all these patents on it, and they, like I said, super excited that they had this compound. And it turns out that it's not Pronocil that acts as the antibiotic. It's what happens to the Pronocil once your body metabolizes it. And so, interestingly, when you metabolize the Pronocil, it actually gets converted into this compound called sulfanilamide, and that is the active antibacterial agent. And so this was not under patent. You could purchase this by the bucket load. It was easy to make and not patented. And so people were able to make this and use this as antibiotics, and it found a real application during World War II. Soldiers would have, medics would have tons of this stuff, and if somebody got wounded, they would just sprinkle this stuff onto the wound, wrap it up, and get them to a hospital, and hopefully reduce the risk of infection. And it did. It reduced the risk of infection. Now, there are a lot of variations of this, and so there are still modern sulfa drugs. Usually, you don't just treat somebody with sulfanilamide. You can treat them with derivatives of this, where you have replaced certain components on this to make it so it's more soluble. It goes to certain tissues, but it is one of the classes of antibiotics. The other classes we've talked about. We've talked about the beta-lactam, like the penicillin derivatives, and the cephalosporin derivatives. Those are other classes. Well, this is in its own class. It's a little bit different. And it inhibits the way that bacteria use folic acid, and it just essentially kills the bacteria, which that's really cool. And then here is para-aminobenzoic acid, which it would actually mimics that behavior in those bacteria. All right, so that was our first real antibacterial drug that was synthetic. All right, there are other sulfa drugs that are derivatives of these, and they are a little more nuanced and have been used over many decades. Some of these have shown some antibiotic resistance, and it's not really the drug's fault. That is our fault for overusing some of them, but it's one of our many pathways to treating bacterial infections. So we need more ways to treat bacterial infections, and so that is an active field of study, looking for new classes of antibiotics that can be used, because some of our antibiotics or some of the bacteria have antibiotic resistance, and there are certain kinds of staph infections that are resistant to most of our known antibiotics. So that is an active field of study, and if it's something you're interested in, you should study more chemistry and get good at that. You could change the world. All right, that is the end of chapter 23. Stay tuned for chapter 24. Chapter 24 is coming up soon.